Hi. So in this video, we're going to do an AC analysis of this circuit here. This is a common source amplifier with a voltage divider biasing. So we're going to figure out what the expressions are for the ZI, that's the input impedance seen from the input signal, ZO, the output impedance seen from the output side, VO, and then the voltage gain, AV, and current gain, AI. All right. All right, so as usual, whenever we're doing an AC analysis of a circuit, these are the three common things that we have to do first. So we have a DC-based circuit. This is our original circuit. We need to convert it into an AC equivalent circuit. So we need to short all capacitors. So there are three capacitors here, C1, C2, and CS. And at the frequency of interest, we can assume that the impedances of these three capacitors are at 0 ohm. Okay. So just remember the impedance for a capacitor is 1 over j omega c. So if F is large enough, then 1 over very large is close to 0. So that's the idea. All right. So then we have to also zero all DC sources. In this case, there's only one. That's the VDD at the top. And then we replace the transistor with an AC equivalent model. So in this case, we have this N-channel JFET, which we are going to use this very simplified AC equivalent model, right? So we have a dependent current source here, GM VGS, and that's the gate, that's the drain, and that's the source. All right. So let's do that first. Let's have a look on the right hand side. So remember that CS and C2 are both going to be short. All right. So when CS, especially when it's shorted, RS is going to be bypass. So another name for this particular capacitor is called a bypass capacitor, all right, or shunt capacitor. So the idea is current, because at the frequency of interest, this is a short, so therefore currents will just flow through CS instead of RS. So therefore RS will just will not have any effect. All right. And then on the other side of RD, the top side of RD, this is going to be 0 volts, which means it is going to be grounded, which means that RD, one side of it is going to be connected to ground, down here, and the other side is connected to drain. Okay, so let's have a look how that looks like here. All right, so you have RD connected to ground. So this is the ground part. Okay, so on the source side, notice there's no RS because it's been bypassed. So one side of RD is grounded, the other side of RD is connected to drain. Okay, you still have the VO, you still have a ZO, that's the impedance seen from the output side, and you have an IO. So IO is defined in this diagram as flowing down towards the drain. So when you flip the RD to the other side, then IO also flips, points up instead of down. Okay. And then on the input side, if you remember, there is no current going into the gate. Okay, so and VDD becomes 0 volts, which means the top part of R1 is now grounded. And since R1 and R2 shares the same node in the middle, that means R1 and R2 becomes in parallel, right? Because the top part R1 is now sharing with the bottom part of R2. So therefore R1 and R2 becomes in parallel. And C1 disappears, so it looks something like this. So R1 and R2 in parallel. ZI is still ZI. II is still going towards the gate, right? So going towards the gate, and you still have VI over there. All right. Okay, so let's as usual, let's just define II, IO, VI, and VO. In this case, it's not going to be completely defined, but we're gonna start from there, right? So if you look at II, so this is basically just Ohm's law, all right? So I equals V over R. So the V in this case is VI, all right? So that's VI. So let's start VI first. Divided by ZI. So ZI is the input impedance seen from VI's perspective. Okay. So that's our ZI. We'll expand II in a bit once we figure out what VI and ZI's are. All right. Okay. And then let's have a look at IO. Well, IO is over here. Now, IO is a current that flows this way, going up. through RD. And since there's nothing on the right, so it'll go towards the left, comes down here, and therefore is actually GM VGS. So IO is actually GM VGS, and it's in the same direction. So therefore, IO is simply GM VGS. Okay. Just a reminder, if GM is the transconductance value. Basically, it is the gradient at the point of the coarcent point of VGSQ on the device curve. Okay. Anyway, so mathematically is defined as GM is equal to GMO times 1 minus VGS over VP, where GM0 is basically the value of GM at VGS equals 0, right? So it's just defined as 2 times IDSS divided by the modulus of VP. And IDSS is the saturation current of the drain source. So saturation point of the drain source current, right? So that's the highest you can go, the highest amount of current you can go. All right. Okay. So that's IO is just simply GM VGS. Okay. Now let's have a look at VO or VI rather. Let's have a look at VI. Well, VI is not really Ohm's law. So by inspection, if you like. All right. So VI is simply VGS. Right. You can see VI is from this node to that node, which is also happens to be the gate node and the source node. So VI just simply equals to VGS. Okay. And then VO. Well, VO, again, we can look at, in terms of Ohm's law, we can say it's the voltage across RD. All right. So this is an Ohm's law part of it. So let's just define what VO is. So V equals IR. I in this case is going to be IO, but in the opposite direction, because our VO is positive pointing up. So if you want to keep a VO that is positive, then the current needs to flow downward. So that means it's opposite to IO. So which means we put a negative sign in front of IO, and then times the resistance, which is RD. Okay. Well, we can expand IO right now because we know what IO is. It's just GM VGS. So therefore, it's negative GM VGS times RD. Okay. So that's the 4 components: II, IO, VO, and VI. So now that we can work out what ZI is, so let's figure out what ZI is. Well, ZI is basically the impedance seen from the input signal towards the right into the system, if you like. And it should be pretty obvious because there's no connection from the gate to the device. So therefore, the only thing that ZI will see will be these 2 resistors in parallel. So ZI is very straightforward. All right. So ZI is simply R1 parallel R2. All right. Okay. So that is ZI. Fairly straightforward. So we can expand. We can expand that later. So II can be, we put that as VGS. We can put that as R1 parallel R2 up here. Okay, let's just do that now. So VI is just simply VGS, right? Divided by ZI, which is simply, well, let's see if it's parallel. Oh, okay, I knew that was going to happen. I need to put a bracket around here. Parallel R2. Oh, that didn't work. Okay, sorry about that. Let me just get rid of this. Start again. Okay, so divided by, open bracket, R1 parallel R2, close bracket. Right. So that's what II is. All right. Okay. All right. So that's ZI. So let's have a look at ZO. Well, ZO, remember, whenever we do ZO, what do we have to do? Well, we have to ensure that VI is set to 0. Yeah. So whenever you do an output impedance, the condition is VI has to be set to 0. The input signal sets to 0. But since VI is 0, that means VGS is 0, right? Because they are the same pair of nodes. So VI is 0, therefore VGS is 0. So if VGS is 0, then GM VGS is 0. That means 0 amps, meaning it is an open circuit. All right. So then ZO will only see RD. All right. So ZO will only see RD. So let me repeat that. Whenever we're doing an output impedance, we zero the input signal. And as a result of that, because VI becomes 0, then the VGS becomes 0. So when VGS becomes 0, then GM VGS becomes 0. That means this is now 0 amps. It is an open circuit. Then the only thing that ZO will see is just RD. Again, ZO is very easy, very simple. All right, it's simply equals to RD. Okay. All right, so now let's work out the other two, the voltage gain AV and current gain AI. So let's start with AV first. Well, AV, or voltage gain, is defined as VO divided by VI, right? So that's what it is. So VO, we have an expression for VO, which is this. Let's come down here, just copy it, divided by VI, which is simply VGS. So obviously VGS cancels top and bottom. So what you're left with is just GM RD, negative GM RD, right? And that's AV. All right. Finally, we have our current gain. Well, current gain is defined as output current divided by input current, right? We have an expression for IO, which is GM VGS, right? So that's IO, and then II is this. So divided by, okay, I'm going to put all in brackets here. VGS divided by bracket R1 parallel with R2. Close, and space. There you go. All right. Well, VGS is going to cancel out top and bottom, obviously, and then R1 parallel R2 is going to end up at the top. So what you're going to end up with is just GM multiplied by R1 parallel with R2. Okay, so that's pretty much it. It's a relatively easy circuit to analyze. So I hope that helps. All right, thanks. See you guys in the next video. Bye.